speaker, we have the president, who actually has put up his hand again to help the society in more ways than one. And he's going to introduce a lovely topic that I used to work every single day, I think, in Analysis of Variance, but generalizations of orthogonal components in ANOVA. Sir Brenton, take it away, sir.
Thank you, Maro, and thank you all for coming to support this talk. My talk structure is very easy. It's about the two-way layout and a representation of orthogonal components in the analysis of variance, according to an article which I published in a very little-known journal called the International Mathematical Journal. And it's a historical discussion of the two-way layout. And if you realize that was later expanded into a book in a lot more detail. I'm also going to talk on a note on the Helmert transformation with work that I'd only come across in the last couple of months with Reza Farhadian from Iran, and he contacted me and asked me to contribute. And then I'll talk about uncorrelated residuals, full rankless and full rank matrices, and some more details. So consider the two-factor model. We've got factor A at R levels, factor B at S levels. And for each cell, we have an observation Yij, where, for example, A is the time of planting, B is the spacing between plants, and Y is the cropped yield. The overall mean of the observations is assumed to be the mean mu grand mean plus an effect due to the ith level of factor A and an effect at the jth level of factor B. I'm using these restraints to do the discussion, and if you want to talk about other restraints, you can have a look at my book, Linear Models, the Theory and Application of Analysis of Variance, to see how they are incorporated. I've already mentioned alpha I is the overall average effect, beta j is the overall effect due to the jth level of factor B. The overall meaning of overall is philosophical in nature, since we cannot often repeat the experiment ad infinitum under exactly the same conditions. But that's what's usually intended when we discuss such a model. For example, if we were talking about seasons of the year, we would have R equals 4 levels. Autumn, the factor A would be autumn, winter, spring, and summer. And for instance, then alpha 3 would be the effect due to spring. But of course, this doesn't take into account climate change or anything like that. And of course, we're not assuming interaction when I discuss this initial discussion broached here. We're used to looking at the usual null hypothesis is that factor A of X is 0 versus an alternative that they're not all 0. And factor B effects are not 0 or versus factor B effects are not 0. And you can lay out your observations in the two-way table, and this is the two-way layout, where this is factor A at the R levels, factor B at the S levels, and elements in the response at Yij in the table. The vector Y is ordered column by column from the two-way layout, so that you have the first column is that first set of observations there, then you start with the next element of the second column, and then till the nth column. And with that ordering of the observations, you can work out the normal you can work out the overall mean vector eta as a linear combination of vectors in that vector representation. So if we were to start with the first element of the vector, eta 1, 1, that would be mu plus alpha 1 plus beta 1. And the next element would be the second observation in the first column of the two-way layout. And that would be mu plus alpha 2 plus beta 1, because it's still the first column. And with this organization of the vectors, you can now see that in the vectors in the alphas, that there is an identity matrix that is appearing here and appearing here and appearing down the bottom. And the ones here for the columns corresponding to the column effects, we've got a column of ones, and then a column of ones, and then a column of ones. So that when you have that representation, you can represent the design matrix X, where eta equals X beta, in the form of ones in a first column, and then identity matrices of order R, and there'll be S of those, and then they'll have a column of ones, which is represented by a bold one with R subscript, so that's an R by 1 vector of ones, zeros, 1R, etc. down to the bottom. Now, just let me get something to drink. Okay, so eta is expressed in terms of a linear combination of the columns of the matrix X, and the usual thing is to say that eta's an element of the space spanned by the columns of X. The next hurdle we have to look at in this discussion is Kronecker products. And I'm not sure how many of you are familiar with them, so I will just briefly discuss them. The matrix M can be U by V, and the matrix N can be W by Z, and the matrix M Kronecker product N is then the elements of the matrix M multiplied by the matrix N in blocks, as you can imagine they would be. There's M11 times the matrix N, M1V times the matrix N. It's then a result that you get a bigger matrix, which is UW by VZ, made up of UV submatrices, where each submatrix is a scalar multiplication of an element of M with the matrix N. See that all we need to do the discussion in this presentation is that M Kronecker product N transpose equals M transpose Kronecker product N transpose. You can convince yourself of that if you want to. And M Kronecker product N, U Kronecker product V being other matrices. So long as you can multiply it, the matrices becomes MU Kronecker product NV. We say the matrices are conformable if you can do that. Kronecker products are historically discussed in Searle in 1982 and Rao in 1973. And you have now the possibility of seeing the design matrix in terms of Kronecker products. Because if we go back to this matrix here, that's 1 times the identity, 1 times the identity, 1 times the identity. So we can see then that this becomes 1S Kronecker product IR, and similarly you've got IS, the identity of order S Kronecker product 1R. So that's the basic representation of the design matrix in Kronecker product form. Now, of course, all this is leading to things such as the randomized complete block design, which can also be represented in the two-way layout. And we, for instance, may have S blocks where the plots within the blocks are similar, whereas the plots between different blocks are different to each other. And we have R treatments, which could, for instance, be R levels of fertilizer, and we allocate them randomly within a block, because we want to cover all the bases in terms of if the block had some different grade of fertility down one block, then that would be randomly taken care of by the randomization. In the end, when you record the data, you end up putting the layout as a two-way layout. And the mathematical model is the usual one, that you have the observation is equal to mu plus alpha I plus beta j plus an error, which is assumed to be normal, independent, with mean 0 and variance sigma squared. And consequently, we have, with our vector y being the usual vector ordered column by column, you have that y equals x beta plus e. The vector e here is the vector of eij's with the same indices for the ij's as the yij's. Okay, so when we do the least squares estimates of and for the particular parameterization we've chosen, we've got the average, overall average is our estimate of mu. The estimate of the ith treatment effect is the ith row mean minus the overall column, the overall table mean. Similarly, beta j is the column mean minus the overall mean. And then we have that the residuals are, in terms of the observations, yij minus yi dot bar minus y dot j bar plus y dot dot bar. And the sum of squares of the residuals is then this particular sum here, which I've denoted through by S omega. And this leads to our usual two-way, this leads to our usual analysis of variance table, which is taught to us in undergraduate courses, in some undergraduate courses, I would say. The terms here are for the source of the variation is the overall mean is has a sum of squares being rs times y dot dot bar squared. The treatment, well, if we had just factor A and factor B, it would be the same result. The sums of squares for treatments was s times the sum over I dot bar subtract y dot dot bar squared. And the block sums of squares are given there in terms of the y dot j bar minus y dot dot bar squared multiplied by r. And the residual sums of squares is as discussed in that previous slide. And of course, we take the mean sums of squares divided by their degrees of freedom and then arrive at the F statistics, which you're all familiar with. Now, in Irwin, 1934, he was trying to explain the analysis of variance method that Fisher had been putting forward. And he essentially wrote out the sums of squares in terms of the sum of independent variables, Z2 squared plus ZR squared, there's R minus 1 variables there, which are normal 0 sigma squared variables, and subsequently when we sum and square them we get chi-squared variables. And the paper illustrates these contrasts, I'll call them, in terms of Helmert contrasts, although Irwin never referred to them as Helmert contrasts, and he'd rather just write out the coefficients in longhand. And Irwin used a result of Cochrane 1934, which is basically as follows. Given x1 down to xn, independent normal variables, mean zero and unit standard deviation, if you could sum that and square those variables and get q1 plus ... plus qk sums of squares they'd be, and the q's are each distributed as chi-squared with degrees of freedom n1 down to nk, and n equals the sum of the ni's, then the q's are all independent. So that was Irwin's discussion of the independence of the sums of squares in the analysis of variance. Irwin never used matrix algebra, and he didn't refer to the Helmert transformation as such. On the other hand, the Helmert transformation goes back to the derivation of the independence of x bar and the sample variance when we usually have our random sample of normal observations. And with mean mu and variance sigma squared, we estimate mu by x bar and the variance by the usual sample variance. And Fisher acknowledged Helmert for the discussion of the chi-square distribution for this statistic here. And Lancaster, 1965, makes the first reference to the Helmert transformation as Helmert 1876, where the independence of x bar and Sn squared is discussed. So what is this Helmert transformation that I've been talking about? Well, it's basically a matrix. It's described by a matrix where we're setting up new variables w1 down to wn, transpose equal, well, that's so the vector is, it's a column vector, equals hn times this column vector here. And if you notice, the rows of this vector all have length unity. If we summed and squared those terms and added them up, we would get 1. If we sum and square these values, we get 1. We sum and square these values, we get 1. And the actual form for the general row is such as the nth row is given there. And if you also notice that the inner product of any of one of these rows is 0. So when you take Hn transpose Hn, or Hn transpose, because Hn transpose will become the inverse of Hn, that will be the identity. Now, you might have seen this matrix in more familiar terms in this form here, but I've just taken the last n-1 rows of Hn and called them Bn. So essentially I'm taking these rows here from there to the end to form my matrix Bn. And Bn is orthogonal to 1n. And if you use those, I'll go back again. If I use these matrices and write the matrix Hn, which is 1 over root 1n Bn transpose, and just plug them into the relations Hn transpose equals the identity, and Hn transpose Hn is the identity, then you'll come up with a matrix Bn set of relations, which are Bn1n is 0, Bn transpose is the identity of order n-1, and Bn transpose Bn is the identity minus 1 over n times the matrix, which is n by n with ones in it. And that is your usual projection matrix onto the orthogonal space to 1n. And also you can see that W2 squared plus Wn squared, leaving out the W1 can be root n x bar, is written down in this form as x1 down to xn, Bn transpose Bn, x1 down to xn. Because you can write this matrix in terms of the orthogonal projection matrix, and it's not hard to see with the particular vector that this is the sum of xi minus x bar squared, which is usual sample variance. So these W's, which are independent of each other because of Lancaster, 1959, where he showed that if you had a linear combination of normal variables which had zero correlation, then they were independent, then essentially we've got that n-1 Sn squared is independent of root n x bar, or x bar and Sn squared are similarly independent. Okay, so I'll just mention Irwin acknowledges Burnside for that particular result for the simple normal random sample. So there's different people have rediscovered it again and again. Another point is that the recursive residuals are related to these observations, because if you take a new observation xn plus 1, it's possible to evaluate Wn plus 1 as a new normal 0 sigma squared random variable, and the update of the variance is very straightforward. Cox in a discussion of Brown, Durbin and Evans talks about that, and so does Fairbrother in an American Statistician article. Now, the Zs which Irwin came up with can now be put in matrix form. And these are the forms for the mean. You've got this row of ones. For the treatments, you've got an R minus 1 by RS set of rows which correspond to the treatments. These can correspond to the blocks, and these correspond to the error. And the BS is orthogonal to the 1S. And so when you take the inner product of any one of these rows with any other one of these rows, you will get 0. And consequently, you have a complete set of orthogonal terms for which CC transpose is equal to the identity. That's the C here. It's a RS by RS matrix in this particular discussion. The fact is, if we take the covariance of Z, it's C times the covariance of Y, which is sigma squared times the identity, times C transpose, and consequently you get that this is a set of independent observations because they have zero covariance on the off diagonal. Similarly, we can see that if you want to get the Z2 squared plus ZR squared to get them equal to this sum of squares, you can use the form of CT transpose CT, which I give in this matrix here, these sort of matrices here. And it's a matter of matrix manipulations to use those previous relations between BR transpose and BR and BR transpose and 1S transpose, for example. And you get the orthogonal projection matrix onto the treatment space. And it's then possible to write down PTY in terms of what that looks like, and it's equal to 1S Kronecker product times these terms, and you can then see that Z2 squared plus ZR squared is the norm of PTY squared, because PT is an orthogonal projection matrix. It's idempotent and symmetric, and therefore you get this sum of squares of observations being S sum of yi dot bar minus y dot bar. Similar relationships can be worked out with the block sums of squares and with the error sums of squares. And I'll just see how I'm going with time. Consequently, Irwin observed that under the assumption of homogeneity, that is where the variables Z2 down to ZRS have zero mean, when the alphas and the betas are zero, and the sums of squares are independent with chi-squared with degrees of freedom R minus 1, S minus 1, and R minus 1, S minus 1, for example, respectively. Now, you don't have to assume that the effects of the alphas are zero and the effects of betas are zero. You can expand this discussion now using Lancaster's assumptions of zero correlation, but you then get the sum of squares of chi-squared random variables which have non-centrality parameters that depend only on the alphas. For example, if we're looking at the treatment sums of squares. And I'll just, this all comes out of using the form for the design matrix that we have for X and the CT, for instance. And similarly, the block effects can be giving a non-centrality parameter, which involves only the beta j squareds. And of course, this is what we usually tell our students, that if the betas are, if you've got a non-centrality parameter involving only beta and you're testing for the betas being zero, then you get your usual F-test results. Another thing that can be discussed in using this approach is that the identity is equal to C transpose C, but if we were to go back to where we put our C transpose, you get a row of these CT, CE transposes, and consequently you get the usual orthogonal decomposition of the P's and adding up to the identity. Consequently, you can work out that the sums of squares of the Y's is equal to the sums of squares of all those terms, which are the in turn sums of squares of the analysis of variance table. A point to make here is that the error sums of squares, which are BS Kronecker product BRY, sorry, the error contrasts here are in fact the same contrast that we would get if we used Brown, Durbin and Evans discussion of the recursive residuals. So this further emphasizes the historical link between the Helmert transformation and the recursive residuals. There's an article in the American Statistician regarding this, and this goes back to Pizzetti in 1891. Okay, well, I'm now going to talk about some work which Reza Farhadian came to me with just recently, and he essentially took the path that Irwin did, and just to not, I don't mean to do this to confuse you, but it's just the way that Reza had his article written. Now the x's are normal mu sigma squared, and the y's are defined as the contrasts. Okay, so this is the Helmert contrasts in the y's and the x's. And the Helmert matrix representation of that is the vector of y's equals hn times the vector of x's. The Helmert matrix is discussed in my book. Now, Reza was interested in matrices that extend as the matrix size grows by n, such as the Helmert matrix. And fortunately, there's not a large number of matrices that satisfy this, but based on Akis and Kizilaslan, 2019, and Farhadian in 2019 in Communications and Statistics, the particular matrices they came up with were of this form here, where the alphas and the betas could be either plus or minus 1 or plus or minus 1. So that's formula 7 that the matrix is put as. And the Helmert matrix is the choice of alpha equals beta equals 1. That's the usual Helmert matrix. But their generalization is there with plus or minus 1 and plus or minus 1 for beta. Now, you'll see that, I'm going backwards, I should go forward, sorry. The proposition that Reza came up with was that using the contrast written out longhand like this, that for alpha equals 1 and beta equals plus or minus 1, that we have the usual decomposition of the x's into from normal mu sigma squared variables into a normal root n mu sigma squared random variable and n minus 1 other variables, which are IID normal 0 sigma squared. And then he had for alpha equals plus and minus 1, beta equals plus or minus 1, that the x's are, if they're IID normal 0.1, then the y's are also IID normal 0.1. Now, it is clear, according to Reza, that the matrix HN dot dot is orthogonal. I'm not sure if that's easy to see, but I'll show you in a minute how to do that. For alpha equals beta equals 1, you get the same transformation that's usually talked at as I have discussed it, for instance. And the proof that Reza gave was a little bit detailed, and he got all the terms and added them up and showed that the expected of the yi's from 2 for I equals 2 to n was 0, and then the variances were equal to sigma squared for part A of that proposition. For part B of the proposition, he considered calculating all these terms again. And this is the approach that Irwin took in a very detailed analysis in his 1934 paper, but Reza's repeating it again for this particular generalized set of HN. There's some remark on the fact that the for alpha equals minus 1, beta equals plus or minus 1. If n is even, then y1 is normal 0 sigma squared. If it's odd, you get y1 is normal mu on root n sigma squared. And for alpha equals minus 1 and some other conditions here. The matrix approach to this is to realize that that matrix Hn umlaut, which was this matrix here, is actually just U times the Helmert matrix times V transpose, where U is the diagonal of 1 beta down to beta n minus 1, and V is the diagonal of 1 alpha down to alpha n minus 1. And it's clear that with alpha and beta just being plus and minus 1, I'm sorry about the order of this, but the betas come before the alphas in this. The matrix Hn dot dot is orthogonal because if you take Hn dot dot transpose, then it can be seen fairly easily that these are orthogonal matrices. VV transpose is equal to V squared, in fact, which is the identity, and UU transpose equals U squared is equals the identity. And so you get that the identity falls out when you multiply the matrices together. And of course, I'm going the wrong way. Therefore, if we multiply out covariance of Hn dot dot times the x's, which are the normal mu sigma squared random variables, then we get Hn dot dot times the covariance of the x's, which is sigma squared times the identity, times Hn dot dot, which equals sigma squared times the identity. And so we can then say, according to Lancaster in 1959 in the Australian Journal of Statistics, I might add, that you have independent normal variables with variance sigma squared times identity. Now you don't, that's if we want matrices which have a sort of a lower diagonal form. If you might realize that you can take any matrix U and any matrix V which are orthogonal, and one I choose is where I swap the ith and jth row of the identity matrix, and that's my U, and that essentially swaps the ith and jth row of the Helmert transformation that you do multiply that out with. So I'm going backwards and forwards. And in fact, if you go back to those relationships which I talked about before, Bn 1n equals 0, Bn transpose equals the identity, and Bn transpose Bn equals the orthogonal projection matrix under the error space. You can take any orthogonal projection matrix of order n minus 1 and multiply it by the Bn to be our Bn tilde. And if I substitute Bn tilde into any of those relationships, they get the same result, because Qn minus 1 Bn times 1n is 0, because Bn 1n is 0, for example. So the generalizations of those contrasts are easily possible. I didn't do them in my book because I just wanted to explain, as did Irwin, that you could come up with some contrasts such as those explained by the Helmert matrices. Consider the linear model for uncorrelated residuals. Now, here I'm going back to the usual form of our linear model, y equals x beta plus e, where the errors are normal 0 sigma squared times I. In a paper, Godolphin and DiTullio in RJRSSB, they showed that all the matrices that we can think up for the errors, for the residual space, where Cx equals 0 and Cc transpose equals the identity of order n minus k. So it's it's the bottom, in terms of our two-way layout, that would be the C matrix, which is BS Kronecker product BR. But you can relate it to any set of other matrices, and they're all related to each other. In this paper that appeared eventually in 1992 in Communications and Statistics, that set of relationships is generalized to less than full rank matrices, which is the case of experimental designs. And we use that to talk about a general form for a specific type of test of heteroscedasticity in experimental design, which is based on the recursive residuals. And in Janet Godolphin, in 2009, published a paper where she extended this further again, where if you took a new observation and included it into the linear model, but that new observation increased the rank by 1, then you could similarly formulate the relationships between the error contrasts. And also, if you think about it another way, you could actually lose an observation where the rank of the design matrix was going down by 1. And that, for instance, could affect you if, say, you had a design that became what is called unconnected. The connectivity of the design is broken, and so you have to analyze the design in terms of separate designs. Godolphin and also they're publishing with their son now, so I'm not sure. So Godolphin trio, I'm not sure what they've come up with next, but they are looking at what happens when you lose an observation, and they're trying to prevent that observation being such that you lose connectivity of the design. And they talk about robustness in terms of connectivity of the design. Of course, the error vector E doesn't have to be sigma squared times the identity, and you can also look at the likelihood of the error contrast CY, which is known as what's called the restricted likelihood. Also, it was called the residual likelihood by Patterson and Thompson, but Harville seemed to sway everyone to call it restricted likelihood. In fact, if E had a covariance matrix sigma, then as it would have in the case of models which include variance components, then you can see what happens with these sorts of models in chapter 8 of my book. And there's the reference to the book. It's a Wiley publication. I promised that I would talk about some R, and I thought, well, let's just illustrate some of these relationships. If the betas were plus or minus 1, or beta is minus 1, this is what the matrix U would look like. It would look like the diagonal of this 3 observations here, the diagonal matrix with 1, minus 1, and 1 on the diagonal. The Helmert matrix is of order 3, and Robert Hammerstrand wrote me a function to do that. And this is not included in our article, but we could perhaps include it if it was asked for. And so U Helmert is then U times the Helmert matrix. That percent star percent is how you multiply matrices together in R. So U times H3. And if we can see that that is an orthogonal matrix, we just have to take that result and multiply by the transpose of that result, and we get the identity, which is what we want. And that U Helmert being U Helmert times being U times H3 looks like that. That's 1 over root 3, 1 over root 3, 1 over root 3, minus 1 over root 2, 1 over root 2, 1 over root 6, I think that is, minus 2 over root 6. Going the wrong way again. And if you multiply that U Helmert by V and get U Helmert V, that's also an orthogonal matrix, as you realize when you multiply it out. If you want to look at just V, then you look at H3 multiplied by V, and you get that the matrix is orthogonal again. You can do this with 4 by 4 matrices just by calling Helmert matrix 4 and illustrating, say, UH4 is orthogonal, and similarly UH for V is orthogonal. And just to show you that, yes, and then if we look at H4 times V, that looks like this. So that's an orthogonal matrix. And it, as illustrated there. And switching the rows, well, if I switch the rows, the second and third row of the matrix by pre-multiplying H3 by switch, I just see if switch squared equals the identity there, or switch transposes the identity, because that's a symmetric matrix. And then I get switch times H3, I'll call it H Brent. And if I take H Brent, transpose H Brent, I get the identity. Now, all of this assumes normality, and you're probably complaining about the fact that I'm talking about normal models when I'm supposed to be a robustness person. Well, it's the fact is, if you're looking at models in experimental design with very few observations per cell, even the great Huber writes, somewhat embarrassingly, the robustification of two-way tables is wide open. Typically, there are so few degrees of freedom per cell that the customary asymptotic approaches are out of the question. So there's my defense for doing that. It's also a historical way I learned things. I went to listen to John Darroch and Alan James talk about experimental designs, and you learn all about normality. And it wasn't until I got to ANU and I started reading Hampel's newly minted thesis that that I started thinking about robustness as a reasonable way to go. It's also in Hampel's book, is Hampel's thesis, that if you have only 3 observations, for example, then you probably would use an efficient estimator in order to estimate the mean. So even Hampel was doing that when he had few observations. I just wanted to give a bit of publicity to Rosemary Bailey's latest article, which is on Hasse diagrams. If you go to my book, I've called them lattices because John Darroch called them lattices. And John explained to us he didn't like to call things by people's names, even though he's got a distribution named after himself. And so Haas, according to Rosemary, was a Nazi, and maybe that's why. She suggested that might have been a reason why his name hasn't been associated with the diagrams. But that's another issue. And anyway, Communications in Statistics Theory and Method, Rosemary Bailey's book. She talks about a package that's coming out to draw the lattices, which sounds very interesting. And that is the end.
Thank you.
I haven't. Yes.
Marathon. 51 minutes, Brenton.